record now, just to let you guys know we're recording. And our objective today is to look at two tests. And again, we're still doing it. It might seem like we're just doing the same thing every week. We are. I'm just introducing two more tests today. So today we're going to look at something called the direct comparison test and the limit comparison test. And we're going to use those tests to figure out if the series converges or diverges. For the convergence test, the terms of the series have to be fairly simple, and the series must have special characteristics in order for the convergence of the test to be applied. A slight deviation from these special characteristics can make the test non-applicable. In other words, you can't use that test. So for example, if I asked you guys to determine the convergence or divergence of this, well, it's clearly geometric, so you could use the geometric series test to determine if it converges or diverges, and I think in this case, I think it converges, because r is less than 1. However, if I gave you this problem, you would not be able to use the geometric test. In fact, or geometric series test. If you did, it would be incorrect. Similarly, on number 2, if I gave you a series like this, you would say, oh, that's a p-series. No problem, I can do a p-series. That one's going to converge because p here is greater than 1, therefore it converges. However, look at this series here. Notice that it's very similar. The only difference is this +1. You cannot use the p-series test on this problem. Not directly. And then last but not least, this guy here, this is fairly easy to integrate. You would, again, use U substitution, so you could do the integral test. But if I give you one like this, the integral test isn't going to apply there. But notice how similar those are. The only difference is this power of 2. So let's go ahead and discuss our first type of test that we can use, which is called the direct comparison test. You'll see me abbreviated as DCT, direct comparison test. Here's what it says. In fact, actually, I think last week when we were doing our practice problem on Friday, I think it was Stephen, actually did one of the problems, one of the harder problems. Instead of using the integral test, he actually used this test. So that was actually a really awesome moment. Anyways, so here's what the direct comparison test says. First of all, you'll notice that the A sub n, that's the stuff here, and the B sub n, they both have to be greater than 0. This is only applying to all positive term series. And we need to know that A sub n is less than or equal to B sub n for all n. Now I'm going to let you know that this is a little bit stronger than what we need. We'll see some examples of that, but let's not worry about that for now. But in general, you need all the A sub n's to be less than or equal to the B sub n's. So if we draw a picture of that, I'm going to just kind of sketch a picture using two different curves. And guys, remember, when we're talking about, in fact, I should probably use points here. So let's just say that this guy right here, by the way, these are the green things here. Let's let those be B sub n's. So the green here is B sub n. Guys, can you see those green dots clearly enough on the screen? Okay, awesome. Okay, so there, I can't make them much bigger. It doesn't like that. All right, so now I'm going to do blue, and then these are going to be, oh, I guess I should have done, the green is the B sub n, sorry. So the blue is going to be the A sub n, so these ones have to be less than. I'll try to make these a little bit bigger. In fact, I'm going to make them kind of get a little bit closer together. Anyways, you get the idea. So then the blue is the A sub n. Now, as you look at this, I know this is a very lame drawing, but pretend that these are the different terms of this series. Or if you want, you can even think of it, actually we have to think of these as the actual terms. So this is the first term, A sub n. This is the first term, B sub n, on down the line. Now, obviously, if we're summing those things, then we're going to get numbers that are growing since they're both all positive. But anyway, so that's the idea. So here's the thing. Notice that all the blue stuff is below the green stuff. Agreed? So here's what I'm saying. If the green stuff converges, guess where the blue stuff is? below it, correct? So if all the green stuff converges as we add them together, guess what has to happen to the blue stuff? It also has to converge. Kind of makes sense intuitively, doesn't it? Similarly, but in a different way, remember the A stuff is less than the B stuff. Similarly, if the sum of all the A sub n diverges, in other words, if this stuff on the bottom goes off to infinity, guess what has to happen to all the blue stuff that's above it? It has to go off to infinity as well. It should kind of feel like a very important theorem that I've mentioned in the past, and it's not the same thing, but it's similar. It's that squeeze theorem. You guys remember me mentioning squeeze theorem? It's the same idea. So here's the idea. If the sum of stuff on the top converges, then the stuff below it obviously has to converge too. Now, where you have to be careful is, let's say that you show that all this stuff in green diverges, the stuff on top. Does that mean the stuff underneath it has to diverge? Not necessarily. So notice this is important. If the bigger stuff converges, then the littler stuff has to converge. If the little stuff diverges, then the bigger stuff also has to diverge. I hope that makes sense. That's kind of the gist of this. So let's look at an example, unless there's a question. Okay, so first example here, we're going to use the direct comparison test. We've got a pretty nasty looking function here, and it's 5 over 3k squared plus 2k plus 1, and we're summing it from 1 to infinity. So what I'm going to do here is this, I'm going to say that my a sub n is 5 over 3k squared plus 2k plus 1. I'm going to let that be my a sub n. I'm going to let my b sub n, and I'll do that in, let's do purple. I'm going to let my b sub n be something similar to this. And in this case, I'm going to do 5 over 3k squared. Actually, I'm sorry. I'm actually using incorrect notation here. Let me fix this. Technically, we're not doing n's here. I'm doing k, so this technically needs to be k. Sorry, I'm not trying to be confusing. All right. Now, very important question. Would you guys agree, I'll do this in green, that that is true? Would you agree that all of these terms have to be less than all of these terms? It has to be true, and let me explain to you why it has to be true. First of all, you could just take some numbers and plug them in and you will see. But here's the key. You see that 2k plus 1? I'm adding numbers k that are 1 or bigger. They're all positive integer values. So what I'm doing is these two fractions are equivalent except for this 2k plus 1. So when I add more positive stuff to this denominator, that's going to force that, that value to be less than this value. Does that make sense? Oh, and one more thing. Guess what else I should probably say? Technically it's this, but it's strictly less than, but I'm going to put less than that. And you would also hopefully agree that these are all greater than 0. We need those things to be true. So here's my a sub k, here's my b sub k. My a sub k's are always less than my b sub k's for all real, or I don't even need to say real numbers, I'll just say values of integers. Now, why is that helpful? So why that's going to be helpful is, let's do it in blue, is I'm now going to, instead of looking at this series, I'm going to look at this series right here. Oops, I just wrote the wrong number on top. 5 over 3k squared, which is the same thing as k equals 1 to infinity of 5 over 3 times 1 over k squared, which is the same thing as 5 over 3 summation of infinity k equals 1 over k squared. I hope you guys, I kind of went through that quickly, but that makes sense, right? There's no big surprises there. So the 5 over 3 can be, kind of uncoupled from that 1 over k squared. I mean, that's kind of intuitive. And then we have this property with summations where if we have a constant term like that, that the constant term can come out to the front. And so now we have a very important observation to make. What is that?
P series?
It is a P series, James. That's exactly what it is. This is a P series. And in this case, P is equal to 2, which, by the way, is less than, oops, not less than 1. That would be interesting. We want to break math, which is greater than 1. And since P is greater than 1, we know that it converges. Now I'm going to pause here for a second and let you write that down if you're writing it down. So I have somehow used this, let me go back to the blue I was using. I have somehow used this summation of k equaling 1 to infinity of this b sub n. Remember, that's where we started. This is the, not b sub n, b sub k, sorry. B sub k. We did a little bit of algebra. We got to this, and then we identified, oh, that's a P series. And it has to converge since P is greater than 2. So this converges. So that's wonderful. Now, let's go back to our theorem. Our theorem 812, which is the direct comparison test, says if the bigger series converges, guess what has to happen to the lesser one? It has to converge as well. So did I just show you that the bigger series converged? Yep. And since the bigger series converged, now I can draw my final conclusion. I can say, and here's how I write my answer, triple dot, that means therefore, the sum from k equaling 1 to infinity of 5 over 3k squared plus 2k plus 1, that series converges by the direct comparison test. That's my conclusion. Now, as I am kind of hesitating here to move on to the next example, let me just tell you that I actually think that the direct comparison test is one of the coolest tests. Because here's what we know. I guess maybe I should say we know. Here's what they know. Here's what the mathematicians that came up with this test. I did not come up with this test. Stephen kind of came up with this. Here's what Stephen knows. I figured out that this series of infinitely many numbers converges based on something that's kind of like it, but not exactly. I just think that's amazing. I didn't even list out any terms of this series. And yet I know it converges. I don't know what it converges to. Again, remember I told you at the beginning of this chapter that except for the case of the geometric series and the telescoping series, you normally won't be able to tell me what the sum is. But I do know that it converges. And in order to use this test, it definitely takes, there's a little bit of subtlety to it, right? In fact, you might say, wait a minute, Mr. Allen, you just kind of ripped through that real quick up there at the beginning, and you said, here's A sub k and here's B sub, how'd you know that? By practicing it. You look at this, and first of all, hopefully as you look at it, you're thinking, okay, well, it's not a P series. Right now, it's not. It's not a geometric series, at least not right now. It's not, and it's not, I can't do the integral test on it. So maybe I need to do something else. So we're going to try this direct comparison test. So is there some fraction? I mean, when you look at that, couldn't you kind of guess it converged? I mean, the top is 5, and the bottom is some polynomial with all positive numbers, right? Growing. it seems like it should converge. I mean, that's our intuition. Now be careful, sometimes that can get you in trouble. So it felt like it was going to converge. So then what I tried to do, this was the key right here. This is the key, is picking a b sub k in such a way that I can figure out, oh yeah, that's a convergent p-series. And all of these terms are greater than those terms. And if this converges, that forces that to converge. Yeah, I think I've chatted enough about that. Does anyone have any comments or questions about this example? Okay. So I'm going to go ahead and move on then. Is this series convergent? And then it says explain. What's your gut instinct on this one? Just looking at it, what's your gut instinct? Do you think it converges or diverges? You may not have, you may not even be able to have a guess.
Can you get rid of the n on the bottom?
How?
Just because ln of n is bigger than ln of n over n.
Oh, are you saying can you just cancel the n's?
No, just like a direct comparison test. If you ln of n is going to be bigger.
Do you think that this converges or diverges?
Well, it would converge because ln of n
grows slower than n. Is that what you're thinking?
Yeah.
Yeah, you would think that, right? And Gavin, I'm just letting you know, you'd think that, but unfortunately, guess what? You're wrong. And I'm not saying that with joy. I'm just telling you, honestly, if you asked me just intuitively to guess, do you think that converges or diverges? I would tell you, I think it converges too. But it actually does not. It diverges. So look at something. Yeah, there's a poll question there if you want to. Oh, Alex, go ahead.
I hit it by accident.
By accident? Okay.
Yeah.
So let's go ahead and look at this one. So I'm just going to cheat here a little bit, and I'm just going to tell you that this guy diverges. And I'm just telling you that I picked this one on purpose because I think that most of us would think that it converges. So since we know it diverges, if we come back to our theorem, if we want to, we want to show that our b sub n is divergent. So what I want to try to do now is I want to try to figure out, so I'm going to let this be b sub n in this case. So notice that in my first example, I let my my a sub, this right here, I'm trying to be careful with my words, the stuff in the problem to be the a sub n, or in the last example was a sub k. In this example, I'm actually going to let it be the b sub n because I'm trying to show that it diverges. And in this case here, I'm going to let my a sub n be 1 over n. Now, first of all, I would like you to know that you would agree that for n greater than or equal to 1, those are both positive. Agreed? What about here, though? Would you guys agree with this? Now, if you're not sure if this is true, something that you can do is you can literally plug 1 over x into y1, and y equals the ln of n over x. Sorry. You could plug these two functions into your graphing calculator and then go to the table and then just compare. Now, the truth of the matter is, if you're not too careful here, for n equals 1 and for n equals 2, this is not true. Right now, this is not true. This is true for n greater than or equal to 3. So once you get to 3, this is always true. So earlier, in fact, let me go back to that slide again. I said for all n, and if you remember, I said that's a little bit stricter than what we need. And here's what I mean by that in this case. Remember, how many terms are we adding together? Infinitely many of them, correct? So my point that I'm trying to make here right now is, do the first couple of terms really make a big difference in this example? By the way, both of these numbers are pretty small, right? Those first two terms aren't probably going to affect whether this thing converges or diverges. So in this particular case, in fact, I'm going to erase this work that I've done here now. I'm going to get rid of this, and I'm going to get rid of this, and I'm going to get rid of this up here. And I'm telling you that this is true. This and this are greater than or equal to 0, and this is always bigger than or equal to this as long as the n is greater than or equal to 3. Okay, so let's go ahead and move on. So, what is the sum, starting with 1 going to infinity, of our a sub n? In other words, what is our sum from 1 to infinity of 1 over n? Well, hopefully you guys recall that this is the harmonic series. And what do we know about the harmonic series? It goes to infinity. It diverges. The harmonic series, which is one that, again, is one that I would not think diverges, but it does. Okay, it looks like you guys have answered the poll there, and most of the answers are correct. It's the second option. This diverges, so now I can draw my conclusion. Therefore, this series that we're interested in, a sub 1, or n equaling 1 to infinity of the natural log of n over n, diverges by the direct comparison test. That's my conclusion, based on the fact that this a sub n, which I picked carefully, I know that this diverges, and then I know as long as n is greater than or equal to 3, this will be less than or equal to this. So if this series that's below this series diverges, then the one above it has to diverge. In fact, let me go back to that example right here. This blue thing here, you can think of that as that 1 over n series. So we're adding 1 plus 1/2 plus 1/3 plus 1/4, blah, 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 blah. Above that, now here's the interesting part on this one, and I've actually got to fix this picture here just a little bit. It turns out that I think the first term actually might be 0, and then the next one's kind of screwed up. It's not till we get to n equals 3 that we actually get everything up above. So this is, if you will, kind of what that graph might look like. So this blue series, which I'll call up here in blue, this is that natural log of n over n. That's what that series is. Did I draw those backwards? I did. I screwed that up. The green series, that's the natural log one. I did that backwards, guys. I'm sorry. Nice job, Mr. Allen. Thank you for confusing us. Let's do it in green. So green here, this is the natural log of n over n. This is the sum. So if the series in blue, this should have been blue here. Let me do it in blue. If this blue series, which by the way, down here on this side, notice the blue is below the green. If that blue series is going off to infinity, then the green series, which is above it, also is blowing off to infinity. Anyway, so there's the word. Okay, comments or questions on that one?
So you said at the beginning, you said n is greater than or equal to 3. Can that
Correct.
be like n is greater than or equal to 50 as long as this b sub n?
Yeah, and that's it. Yep, you're absolutely right, Gavin. And here's kind of the crazy thing, guys. And I was actually, anybody have Mr. England by chance anywhere along the way? Mr. England for pre-calc? Okay. Mr. England and I have been spent a little bit of time together walking early in the morning. Anyways, was talking to him about Graham's number, and I think I've mentioned that number to you guys before, how big that number is. In fact, it's been around since 1971, which happens to be the year I was born. The number is so out of reach for mathematicians and computers that Graham himself said that it's unlikely that we'll ever know the leading digit of Graham's number. Okay, that number is almost 50 years old. They think of all the technology that's available. They know some of the ending digits, but they can't even, this is a finite number, but it's so big that they will likely never know the leading digit. So what Gavin is saying is, hey, Mr. Allen, what if I just need to show that it works for n greater than 50? The answer is he's correct. Guys, 3 is nothing compared to infinity. 50 is nothing compared to infinity. Now, guys, I'm telling you, I can't think of an example of when you would have to get, n to be bigger than 50. But sometimes early on in the sequence, you might have to adjust, maybe a 3, or usually it's maybe even just 2. But yes, that's correct, Gavin. Jack.
Speaking of that being greater, could we also use that to manipulate the integral test? Because I know it's supposed to be greater than 1, but could you use it to be greater than 3, or does it have to be greater than 1?
I think you would just need to check that the front end doesn't go off, doesn't diverge. As long as the front end of the integral doesn't diverge, I think you're okay. So I'm being very careful with my words right now. And Jack, what I think you're saying is correct in most cases, but we got to be careful because there are some functions that they don't diverge as you go to infinity, but they actually could diverge between 0 and 1. But yes, in general, I think, or I shouldn't say general. In most cases, yes, I think you could do that.
Okay, because my first instinct for this problem is it looked like I could use the integral test because of U sub.
Wait a minute, what screws up with the integral test? Oh, 0, no, 0 is okay. 1. Okay, what do we need to know for an integral test? It has to be
Positive,
continuous,
and decreasing.
It's not decreasing though, is it? I think the problem is it's not decreasing. I think that's why you cannot use the integral test. If I'm not mistaken, and you guys can check. In fact, let's all do that real quick here. That's a great question. If you would humor me, take your calculator, set your window from, let's say, I don't know, let's just say from 0 to 10. And then my y min, I'm going to go from 0 to, actually, I'm going to go from -1 to, I don't know, 5. And I'm going to plug in the natural log of x divided by x. I'll make sure there's nothing in this other graph. Clear on the hit graph. Yeah. You see how it's not decreasing initially? So the integral test would not apply here. So you'd have to, now you might say, well, wait a minute, and this goes back to Gavin's point. Hey, what if I just set n is greater than 3 or whatever once it starts decreasing? I think in order for you to use the integral test, technically you're supposed to be, it has to be true for n equaling 1 and greater. But anyways, good questions. Good questions. And I'm not, please, the answer I'm giving you, Jack, don't write that down as holy gospel because I am nowhere near, I'll be honest, I would have never come up with some of these tests. Like what Stephen did last week in the practice stuff. Stephen, I'm giving you kudos. Someone had to tell me about the direct comparison test for me to figure out the direct comparison test, and you kind of figured that out on your own. So, okay, let's go ahead and move on. We've got one more test to discuss today. We only got about 15 minutes left, so I've got to pick it up. The good news is this one's actually a little bit easier to understand and a little bit easier to apply. And it's actually very powerful. In fact, it's one of my favorite ways in terms of efficient ways. I mean, obviously, if it's a geometric series, that's super easy. Or if it's a p-series, those are like easy. This is called the limit comparison test. So it says sometimes a series closely resembles a p-series or a geometric series, yet you cannot establish a term-by-term comparison necessary to apply the direct comparison test. Now notice it says term by term. I kind of skipped over this, But remember, it said for all of them, and in the last example, we had to start at 3 to be able to use it. But in general, you want all the terms to kind of fall underneath or above. Under these circumstances, you may be able to apply a second comparison test called the limit comparison test. So the direct comparison test I call DCT, limit comparison test is LCT. And here's what it says. Here's the requirements. We just need both the A sub n and the B sub n to be greater than 0. And, keyword is and, if the limit of their ratio is equal to L, which is a finite positive number, then they both either converge or diverge. So let me say that again. We need the A sub n and the B sub n to both be greater than 0. Here's the key. You are going to do the limit as n goes to infinity of their ratio. If that is equal to a finite and positive number, then you can conclude that both of them converge or both of them diverge. So I'm just going to do an example, okay? Because I think it'll be easy just to look at a nice, easy example, which is one that we've seen kind of before. In fact, just looking at that, can you kind of guess which B sub n I'm going to use? I'm going to tell you right now, A sub n, I'm just going to let A sub n equal 1 over 2 to the n minus 1. What do you think B sub n is going to be? Just unmute yourself. What do you think it's going to be?
1 over 2 of n.
You got it. And what do we know about this? What do we know about this sum?
That it's geometric and it converges.
It is a convergent geometric series, right? This converges because it is a geometric series with r less than 1. Agreed? Everyone's good? So here we go. So, actually, let me go back to my slide here. Remember, we need to make sure that everything is positive. Is everything positive here? And is everything going to be positive here as long as n is greater than or equal to 1? Check. Because if you plug 1 in there, you're going to get 1 over, well, that'd be 1. So that's positive. Same thing here. And it's always going to be positive. So everything's good. So here's what we're going to do. So we are going to do the following. I'm going to put arrow, arrow. We're going to do the limit as n goes to infinity of A sub n over B sub n. Okay, so that means that we're going to do the limit as n goes to infinity of 1 over 2 to the n minus 1 over 1 over 2 to the n. Now, when we divide fractions, how do we deal with that? We multiply by their reciprocals. So I'm going to do 1 over 2 to the n minus 1 times 2 to the n over 1. Now here's where a little bit of trickery is going to come into play. Do you guys remember when we were trying to figure out, like, let me do this in a different color. Do you remember when we would try to do something like what's the limit as n goes to infinity, or let's say x goes to infinity of like 2x squared plus 3x plus 1 over, I don't know, 5x squared plus 7x minus 2 or something. You guys remember when we do that? What was the trick for doing that limit? Not the L'Hopital. What would we do?
You could use the horizontal asymptote, and you get 2/5.
Right, that's the answer. But how do you get to the 2/5?
You divide.
You can divide through by the highest power.
By the highest power. I'm going to play the same game here. My highest power is going to be 2 to the n. So I'm dividing through by everything 2 to the n. Let me go back to the green. So this is going to be the limit as n goes to infinity of 1 over 2 to the n divided by, now what's 2 to the n divided by 2 to the n? 1 minus 1 over 2 to the n times, And then I'm going to have 2 to the n divided by 2 to the n, which is again going to give me 1 over 1 divided by 2 to the n. So all I did is I divided everything through by 2 to the n, which was the highest power. You'll notice that this term and that term is going to cancel. So that gives us the following. And guys, I'm showing all the steps here just to make sure that there's no confusion on how I got this limit. So now we're left with 1 over 1 to the 2 to the n, which by the way, as n goes to infinity, that's equal to what?
It's 1.
It's just 1. And now I'm going to make a note. This 1 is finite and it's positive, isn't it? And since it's finite and positive, which is what my theorem requires, then it says either both series converge or diverge. Well, what did we establish up here about that series? Well, we established it was a geometric series that converged. So guess what we can now conclude about our original series? It converges. In fact, I've kind of ran out of room here, guys. I'm sorry. I'm going to write it in red. So I'm going to put therefore dot 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 the summation n equals 1 to infinity of 1 over 2 to the n minus 1 converges by the limit comparison test. Guys, I have one more example left, but we're about 5 minutes away from that 60-minute mark. And just if I can get, I'm going to do one more example. And if you would like to stay, I would love for you to stay and see it. But if you've got things you got to do, you can do that. So before you leave, though, please do the exit ticket and hear what I'm getting ready to say. Okay. First of all, don't forget that tomorrow we have a quiz. Okay, so you need to be here tomorrow and logged in and all that to take a quiz. The other thing is that next week, my son, Henry, he's just over 1 year old. He's going to be going to Riley Hospital and having a surgery. And so I'm not going to be here next Thursday and Friday. So I need to be home with my son and my wife. So I just want to let you guys know that. I have a sub lined up that will be here. She actually has a master's degree in math. So she will be more than, I'm going to send her my notes and things like that. She'll be more than able to help you with questions and move on. But I just wanted to let you know, because you guys that have had me for a couple of years, you know that I don't miss very often. And I'm not missing for a frivolous reason. So I just wanted to let you guys know that I will not be here next Thursday and Friday. So, okay. Okay. So exit ticket is in the chat. Please complete that before you take off. I've got one more example that I want to do, and then we'll call it a day. And if you want to stick around during the support time, obviously I'm available. It says, Bill claims that the series below converges. Is he correct? Why or why not? So, you know, this is just another example of a series that you've got to figure out if it converges or diverges. Bill claims that it converges, and we're trying to figure out if he's right or not. So I even wrote this, you know, does Bill know what he's talking about? So let's figure out if Bill is on the money or not. You can probably guess that I'm going to use the limit comparison test, which is what I'm going to do. And so what we want to try to do now is, you know, it doesn't really matter what you let this be. I'm going to let a sub n be this 2n squared plus 3n. And then this denominator, I'm just going to leave it exactly as it is. And now I'm going to figure out a b sub n. I want to try to find a b sub n that I can compare this to using the limit comparison test. And so what I'm going to do here now in green is I'm going to think about kind of the important stuff here. So I'm going to write a sub n, and I'm going to use a tilde. And when I'm using this tilde, I mean sorta. In fact, let me make it this way. It's sort of the same. Would you guys agree that this is the sort of the same thing as 2n squared over the square root of n to the fifth? And what I'm doing here is I'm saying is n is large, that 3n isn't nearly as important as that 2n squared. Similarly, this 5, as n is large, becomes not very important. And I could go further here, and I could say, this is 2n squared over n to the, well, that'd be what, 2.5, right? Now, what is n to the second divided by n to the 2.5? Oops, and this is not equal. I'm not saying they're equal. I'm saying that it's similar. Or this is the same thing as n to the 1/2. Okay. So what I'm doing here is I've taken this very complex looking thing and I've kind of boiled it down to the most important characteristics. So again, I said that 3n and that 5 weren't really that important. And then here I just said, well, the square root of n to the fifth, that's n to the 2.5. And then furthermore, well, if that's n to the 2.5, then n squared, those could be simplified to, so we're dealing with this. Would you guys agree with that somewhat? In terms of when n is large, that's the important characteristic. So what I'm going to do now is I'm going to use this over here. So I'm going to call this 2 over n to the 1/2. And I want to make a very important distinction about this. What is this? What is the series 2 over n to the 1/2 as n equals 1 to infinity? Does it converge or diverge?
It diverges.
Because why, Rich?
P-series.
It is a p-series with p equaling 1/2, which is clearly less than 1, so it diverges. Now you can already, I've kind of already tipped my hand here, haven't I? We're going to find out that Bill is incorrect. But now I'm going to go ahead and go through and do the mathematics to kind of finish this off. All I've done so far is I know what a sub n is, and I figured out what my b sub n is going to be based on the important characteristics of a sub n. So now we're going to go ahead and do the actual limit comparison test. So here we go. We are going to do the limit as n goes to infinity of a sub n over b sub n. So in this case, it's going to be the limit as n goes to infinity. Here's my a sub n, which is 2n squared plus 3n over the square root of 5 plus n to the fifth. Divided by, now instead of dividing, I'm actually going to go ahead and just multiply by the reciprocal, and I'll just call that the square root of n over 2. So I kind of skipped a step there. Hopefully you guys can give me a little bit of grace on that. Okay, so let's go ahead and move on. And now I'm going to very quickly start writing things in terms of rational exponents and getting away from the square root symbols. So this is, well, obviously this is 2n squared plus 3n. But then I got to multiply this by n to the 1/2 all over 2 times 5 plus n to the 5th raised up to the 1/2. Now, what happens when I distribute this into the 1/2 here? What am I going to get? Well, I've got n to the 1/2 times n squared. So what would that be?
Into
2n.
2.5.
Yeah.
To the 5 halves, right? Oops, I just wrote 5 instead of 2. Sorry. You guys said it and I wrote it wrong. So the 2 stays a 2, right? But now we've got 2, which is the same thing as 4 over 2, plus 1/2, which would be 5 over 2. So this is going to be n to the 5 over 2. Plus, and then this is going to become 3 to the 3n to the 3 over 2. The denominator is still just 2 parentheses 5 plus n to the 5th to the 1/2. So that's unfortunately not doing us a whole lot of good here. Now, what can I divide by? What is the biggest power I can divide by here? So I'm playing that same game again. It seems like that n to the 5 over 2, doesn't it? If I divide through, so let me make a little note here. So I'm going to divide through, divide by, and I'm going to put n to the 5 over 2. Okay? All right, so that's going to give me the limit as n goes to infinity. So if I take this first term, 2 n to the 5 over 2 divided by n to the 5 over 2, that's just going to give me 2. The second term is going to give me 3 over, so now I got to subtract. What is 3 over 2 minus 5 over 2? That'd be negative 2 over 2, so that'd just be 3 over n. And then when you play the same game on the bottom, you're going to get the following. You're going to get 5 over n squared plus 1, all of that raised to the 1/2. So now we can plug in our infinity. And as we plug in our infinity, let's do it in green. Guess what that 3 over n is going to become? 0, right? What's that 5 over n squared going to become? 0. So the numerator is 2 plus 0, which is just 2. The denominator is going to be 2 times 0 plus 1 square root. So the square root of 1 is just 1. So the bottom is just 2. So again, it's 1. By the way, is 1 greater than 0 and finite? It is finite and it is positive. And remember, we set up here that this series is going to diverge. So I'm going to put it way down here. Therefore, Bill is incorrect. This diverges, and I've run out of room to write that. So hopefully you can write that maybe in your notes. This is going to diverge. So as we kind of finish up here, a couple of final thoughts here. Be very careful about assuming things. Again, as we started this problem, I'm guessing that some of you might have just looked at this and thought, oh, that's gonna converge, you know, because the square root of 2 or of n to the 5th is like n to the 2.5, and oh, that's n squared, so the bottom's got a bigger power, so it's going to converge. Remember, we're not talking about if the sequence converges. We're talking about if the series converges, okay? And in this case, this series is not going to converge. It is actually going to go off to infinity and not be convergent. It's what we call divergent. So anyways, that's the last example. I tried to do kind of an easy one here, a straightforward one. And then, of course, I tried to do one that was a little bit more complex. And then I did the same thing on the front with the direct comparison test. I'm going to stop recording right now. I hope I started recording at some point. That'll be a good idea.